algorithms, the one we're doing, and there's sort of a nice story from Wikipedia, which you can read about the history about why he wanted to call it dynamic programming. I thought I'd put that up there to do it. But they're actually doing multi-stage decision problems. They were sort of doing something slightly more complicated than we were doing. They were doing indefinite horizon problems. They're doing it going on forever. But now you know what that means. So now you know that we were doing finite stage ones now, and there were ones that go on forever. So this was the classic dynamic programming algorithms that we're talking about. All right. All right. So, whoops, let's do this. Assignment 4 is due in 2 days' time. Please read Piazza, go talk to the TAs. It's not meant to be difficult, but it's not meant to be something you can sort of just do the night before. It's meant to be something you try and you struggle and you say, aha, now I understand. Are there any questions about anything? Okay. So far we've been looking at this representation of a decision network, which is a directed acyclic graph with decision nodes, random nodes, and utility nodes. There's a range for the decision and random nodes, has a unique utility node. And what's important is the arcs in the decision node represent the information that will be available when the decision is made. For each random variable, it's a factor representing the conditional probability for the random variable given its parents. There's a factor for the utility node, and there are no factors associated with decision nodes. Okay, are there any questions about that at all? And then we did variable elimination for creating an optimal policy. And so here, the algorithm is you're going to construct a factor for each conditional. So this is where we ended up last time. We created a factor for each conditional probability table and a factor for the utility. And we summed out the random variables as the not parents of a decision node. We selected the decision variable D that's only in a factor with some of its parents. We eliminated D by maximizing, so we summed out the random variables. We eliminate the decision variables by maximizing the returns both an optimum decision function and a new factor. And we keep just repeating this until there are no more decision nodes. Then we sum out the remaining random variables. Okay, are there any questions about that? That's what we did last half of last time. And as you can guess, I'm going to give some clicker questions. And so we want to make sure there are any questions asked beforehand any puzzlements before we ask them. Does anyone have any questions? Of course, the aim of the clicker questions isn't to actually examine you, but rather to find out what you understand or not. Okay. So here's a decision network. It's the same one we saw last time. It's about buying a car and working out whether it's a lemon or not. The question is, which random variable or variables is or are eliminated, summed out initially before the first maximization? Remember, in this algorithm, we created a factor, now we're summing out, and we haven't got the decision. We want to know which variables we're going to sum out. Okay, how are we going? Does anyone need more time? Anyone need more time? Okay, 3, 2, 1, we'll stop. Yes, the answer is C. We're not going to sum out result, because result is a parent of a decision node. Right, we're not going to sum out result. A and B are wrong. We're not going to sum out results. We're only going to sum out variables that are not parents of a decision node. Okay, so we only sum out lemon. Any questions about that? And the reason we're going to sum out lemon is because we can't use it when we're optimizing by. We don't know whether it's a lemon or not. Right, so when we're going to maximize by, we're not going to know that. Any questions about that? Now the story is we're going to sum out lemons, so now we've got to multiply some factors. Which factors get multiplied? How are we going? Does anyone need more time? How guys, anyone need more time now? Okay, 3, 2, 1, we'll stop. Oh, that's exciting. We've got to multiply all the factors that contain lemon. Which factors contain lemon? Well, what factors are there? What factors exist? For every random variable there's a factor. There's the probability of lemon, the probability of result given lemon and test, and there's a utility function on lemon and bi. Right, so we did this last time. This is what we got. What do we do when we have lemon? We eliminate lemon. We find all the factors that contain lemon. We multiply them. Right, which factors contain lemon? Well, all of these three do. So we multiply these three together and we sum out lemon. So the answer here is C. They don't even look the same. Okay. Any questions about that? All right, this is all of them where they contain lemon. We now know what good questions for exams there are, don't we? All right. Other questions? We're just going to go through the algorithm. After eliminating lemon, a factor on which variable or variables is created. So what's the factor on that we create? So we're a little bit way through this algorithm here. Actually, we're just at the first line of the repeat. We're summing out a random variable, creating a factor. I want to know which factor is created. A factor on which variables is created. How are we going? Does anyone need more time? Does anyone still need more time? Okay, 3, 2, 1, we'll stop. Oh. That's exciting. Oh, look, it's this. So what we're getting rid of lemon, so we end up with some factor on result. This depends on result. It depends on test. And it depends on bi. So this is some factor on result. If you change the result, you change this. If you change the test, you change this. And if you change the bi decision. We haven't even got to decision networks yet. We're only doing variable elimination. Right? You should know this. It's what we did before for belief networks. So the answer is, where am I? Result, test, bi. Which one's that? C. Oh my goodness. At least the mode. Okay, this is just what we've been doing before for variable elimination. All right, so if you change, think about this way. If you have this product, if you change the value of test, you're going to change the answer for this. So test is a value for this. Now, if you change by, then you change this, so you've got to change the product. If you change, right, we're summing over all the values of lemons, so we're going to look at both values for lemons, but it depends on all of these things, result, test, and by. Any questions about that? All right. We now got to which decision variable is eliminated first. So now at the second one, we've summed out the random variables, and we've got this factor. I want to know which decision variable we can eliminate next. Okay, how are we going? Does anyone need more time? We've got about right. 3, 2, 1, we'll stop. What? That's the wrong answer. You guys. We're selecting a decision variable that's in a factor with some of its parents. That's only in a factor with some of its parents. By doesn't have any parents. No, sorry. Test doesn't have any parents. So it says here, in a decision variable, it's only in a factor with some of its parents. Right, this one here is only in a factor with some of its parents. The only thing that's in the factor is some of its parents. The answer here is by. By, this thing here is a subset of the parents of by. This is a subset of the parents of by. But test is in a factor with other things that aren't parents, right? Test is in a factor with non-parents. We can't maximize it. It's only in a factor with some of its parents. Right, so this is in a factor with some non-parents. This is only a factor with parents. Right, so this one here, so the answer here is by. We have to maximize by now. We can't maximize test because we don't know what the result is going to be. Right, we can't say if the result's going to be good, we're going to do this test. If the result's going to be bad, we're going to do this test. We can maximize by because we know what the results in the test are. Yes?
So this is kind of the opposite of random variables, because with random variables, you mention of if they're parents of things, but not children. Sum out parents for random variables.
No, you can variable elimination, you can sum out children or parents. You can do either. Here we can only maximize this if it's in a factor with... Yes, they're more limited. You can't eliminate them arbitrarily. We have to effectively eliminate them backwards. We're going to eliminate the last decision first and the first decision first. And this one here selects the last one. And the last one is in a factor with just its parents. In fact, the whole reason that we did this funny definition of no forgetting is to guarantee that we could actually do it. Right? So we want to here. So we end up with this factor on result, test, and by. And at this stage, we can maximize by because we have its parents in a factor. Okay, any questions? Yes?
How come those
Yeah, we're going to go backwards. We're going to do the very last decision first. We can't maximize test at the moment because we don't know, but we can maximize by. So we're going to go backwards. It's like regression planning. It's a dynamic programming. It's going backwards through time. We're looking at the last one first. What maximizing does? Yeah, so if we have, let's do this. Let's do this. So when we had this one, let's solve this. Let's optimize decisions. So in here we had these three factors. And which variable, there's only one decision node. So what can we sum out? So we have to sum out any variable. Let's move this across to here. Let's move this across to here. Can I do this? Right, so here I want to sum out, which one should I sum out? What should I sum? I want a satisfaction, I want to maximize my utility. Which one here should I sum out or not? Or none? No, forecast is a parent of a decision node. I can only sum out ones that are not parents of a decision node. What should I sum out? Weather. So I should sum out weather. So I'm going to start with the factors. So start with the factors here. Weather umbrella, weather, and weather forecast. So it's forecast given weather, the probability of weather, and the satisfaction given uncertainty in weather. So if we look at any of these, so this is just the weather and umbrella is just my utility function. So now I'm going to sum out this variable, sum out weather, and I construct a forecast like this. Now the question was give an example of maximizing. So what we're going to do here is for each forecast, we're going to maximize the umbrella, the value given umbrella. So we're going to look at the forecast for sunny, and we're going to say, is it better to take it or is it better to leave it at home? If we take it, we get 12.95, and if we leave it at home, we get 49. So we choose the maximum of those two. Right? When the forecast is cloudy, we take it. We can either take it or leave it at home. Leave it at home gives us 14, and leave it at home gives 14, and takes it gives us 5, and choose the maximum value, which is 14. And if it's rainy, there you have a choice between 14 and 7. We're going to choose the maximum. These numbers are sort of a funny mix between probabilities and utilities, because this is sort of the probability times the utility, but we always get to choose the maximum. And then we're going to finally add up the value for this is going to be the sum of those three things. So if we sum this out, we end up with a factor on forecast, we end up with a factor on forecast, which is the maximum of all those three values. That's what we're eliminating it by maximization. But we also end up with this decision function that says, what should we do? So that's when we eliminated D by maximizing. And here, it says returns an optimal decision function, which is and a new factor. So this is the optimal decision function. And this is the optimal decision function, and this is the new factor. We're going to maximize. And we can maximize this only when we know the forecast, because we're going to know we're going to observe the forecast before we act. So we can actually implement this. We can't implement, if I reset the query, weather umbrella, this one. I can't maximize at this stage because I can't decide to take it if it's going to be, leave it at home if it's going to be sunshine, because I don't know if it's sunshine. Right? So I can't maximize at this stage because I don't know. I can't implement this. Right? I can say if it's sunshine, I should leave it at home, and if it's rain, I'll take it, but I don't know. I can't implement that because I don't know whether it's going to be sunshine or rain. I only see the forecast. Okay? Any other questions? Yeah.
So just to clarify, when we maximize by, we're basically setting an outline for like if the test is this way, the result is this way, then we apply an outcome.
Yeah, so this ends up with, let's go back here. So this is sort of like a program. Weather forecast. Hang on, let's sum out weather. Right, this is the program that says if it's rainy, take it, else leave it at home. So it's if rainy, take it. If the forecast is rainy, take it, else leave it at home. That's my function, is a function of the parents. It says what I'm going to do. Okay, any other questions? All right. Let's get back to here. I've lost. Right, so we're going to eliminate by first. We're going to eliminate the last one first. All right. Let's keep going. Let's do the whole algorithm. It might be fun. After eliminating by, which we're going to do by maximization, a factor on which variables remain. So remember, I had this factor on result, test, and by, which is this one. And now I'm going to maximize over by. All right, how are we going here? Do you need more time? Anyone need more time? 3, 2, 1, we're about right. Yay. Test and result. Right, it's this factor. We're going to maximize over this. We're going to have a factor on test and results. We're going to maximize over by. We're going to choose the best by for each combination of test and result. Okay, so we're just going to maximize this. We have some factor. Then we're going to max it. Let's call this F1. So we're going to do max. We're going to do the maximum over by of F1 of result, test, and by. Is some factor F2 of just test and result. Okay, next one. Next question. What is eliminated next after eliminating by? So we've eliminated by. We've got this stage here. Now the question is, what are we going to eliminate next? Are we going to sum out result? Are we going to maximize test? Either one, it doesn't matter, or there's nothing more to eliminate. This is my algorithm. All right, how are we going? Does anyone need more time? All right, 3, 2, 1, we'll stop. Oh. All right. The answer is A. We can't maximize tests. We can't say if the car is good, do this test. If the car is bad, do a different test. Right? We can't maximize tests because that would rely on us saying, if the result is good, if the result is passed, test for the engine, else test transmission or something. Right? We can't do this. The laws of physics and common sense and everything else tell us we can't do this, right? We can't decide on the test depending on whether we pass it or not. Because otherwise, if you're going to get a really good health check, then what you want to do is to get the worst test for something really bad. And if you knew what result you were getting. But what you can do is instead to sum out the result. And then we get just a function on test. So the answer here is A. Any questions about that? So play with these, doing an assignment. I want you to just play with it and work out what's going on because it's not that complicated, really. Okay, any other questions about this? We're going to maximize this. All right. So we're going to end up with a policy. So what does the policy specify? Does it specify just a value for test, just a value for buy, a value for test and a value for buy, or a value for test and a result for buy for each value of test and result, or just a value for buy for each value of test and result? So what does the policy end up being? All right, anyone need more time? We're getting there. Okay, 3, 2, 1, we'll stop. Oh, that's exciting. The answer here is D. It's going to specify both whether we should test and a function of buy from test and results. It's going to tell you a value for test and a value for buy for each value of test and result. Right? C is not right. We're not going to say test the initial and buy is true. We're actually going to say buy if the result is good. Right? And don't buy if the result is bad is the sort of thing we're going to do in here. We're not going to tell you whether to buy or not. We're going to tell you buy conditionally on the result. The whole purpose of doing this result here is to work out whether to buy. The whole purpose of the result is it's going to change whether we buy or not. So effectively here we're generating a small little program that tells us what we're going to do in the future. Okay, and it's going to specify both whether to test and whether to buy as a function of the result. Okay, any questions about that? All right, good. Good. All right, that was fun. That's how we learn things, by playing and doing and testing what we know. Okay, all right. All right, so what we're going to do today is we're going to talk about something called the value of information and the value for control. Actually, this week we're not really going to do anything new. We're going to play with some weird applications and interesting applications of the things we've already learned. We're going to do a little bit about where the probabilities come from. And then we're going to, actually we won't get to the stage of Markov chains. Okay. So first of all, let's look at the complexity of this algorithm. And so we have a decision D has k binary parents. Right, so we have a decision node, D, and it has parents V1, up to vk. And the question is, how many assignments of values to the parents are there? And each of these are binary. How many assignments of values to the parents are there? Sorry, 4? Someone else said, why would there be 4? So they're k parents. And they're each binary. They each have 2 different values. How many are there? Someone said it. A few people said it, but I've forgotten it. How many assignments of values to the parents are there? Right, there are 2 to the k assignments of values to the parents. We could build a big table of v1 to vk, right? And if this had 2 values, say 0 and 1, this could be 0, 0, 0, 0, and then 0, 0, 1, and then all the way down to 0, 1, 0, and 0, 1, 1, and 1, 0, 0, 0, right? All the way down to 1, 1, 1, 1, 1, 1, 1. Right, there's all these 2 to the k different binary numbers with k things. Any questions about that? Okay. How many different decision functions are there? What do we have to do for decision function? Remember what a decision function is. We have to specify a value for this. We've got to fill in this table, right? We've got to fill in this user interface. We've got to give a value for this parent. We've got a value for this parent and a value for this parent, all the way down to here. So how many of those are there? How many different decision functions are there? How many ways are there to fill in this? B. Right, this is B here. And how many ways to fill in this? B, right? So how many ways are there to fill in, if you had just to fill in those 2, how many ways are there? How many ways are there to fill in this B, 2 of them? Right, B squared ways. So how many in total? What is it? So b to the k, someone says. All right. How many parents are there? How many so for each assignment of the parents, you've got to do this. How many assignments of the values to the parents are there? Yeah. Right, b to the 2 to the k.